we have defined the order condition for identification. Order condition is only a necessary condition for identification. Even if it is satisfied, it is not necessary that an equation will be identified. So, we require a necessary and a sufficient condition for identification, and this is given by what is known as the rank condition. A necessary and sufficient condition for identification is given by the rank condition. Let me define what is rank condition in the form of a definition. In a model containing m equations in m endogenous variables, an equation is identified if and only if at least one non-zero determinant of order m minus 1. One non-zero determinant of order m minus 1 can be constructed from the coefficients of the variables, both the endogenous and predetermined, excluded from that particular equation but included in the other equations of the model. This is what is known as the rank condition for identification. So rank condition is that we will be able to construct a non-zero determinant of order m minus 1 from the coefficients of the variables excluded from that equation but included in the other equations. This is both a necessary and a sufficient condition for identification. This is known as a rank condition because, as it is known to you, in the case of a square matrix, as we have defined earlier, the rank of the matrix is maximum number of linearly independent rows and columns. And in the square matrix, we can give a definition of rank in terms of determinants. Rank is if the rank of the square matrix, if the determinant of a m by m matrix is not equal to 0, then the rank of the matrix is m. So if we can construct a non-zero determinant of order m minus 1, means that is the rank of the matrix of the coefficients is equal to m minus 1, then that particular equation is identified. To explain this, we consider a concrete example, then only the points will be clear to you. Suppose that we have a system of equations written as y1t is equal to Suppose that we have a 4 equation system in 4 endogenous variables y1, y2, y3 and y4 and 3 predetermined variables x1, x2 and x3. We first rewrite the system as y1t minus beta 1 0 minus beta 1 2 y2t minus beta 1 3 y3t minus gamma 1 1 x1t is equal to u1t. y2t is equal to minus beta 20 minus beta 23 y3t minus gamma 21 x1t minus gamma 22 x2t is equal to u2t. y3t minus beta 30 minus beta 31 y1t minus gamma 31 x1t minus gamma 32 x2t is equal to u3t. Then y4t is minus beta 40 minus beta 41 y1t minus beta 42 y2t minus gamma 43 x3t is equal to u4t. Rewrite this system like this. Before explaining rank condition, let us first see whether order condition is satisfied or not. K minus k greater than or equal to m minus 1. Now, using the first condition for order condition, 4 minus 1, that is, the equation must exclude 3 variables. Total number of equations y1, y2, y3, y4, x1, x2, x3. So 7. So 3 variables must be excluded means in an equation there will be only 7 minus 3. 7 minus 3 is equal to 4. There will be only 4 variables in an equation. So first equation 4 variables exactly identified. Second 4 variables exactly identified. Third 4 variables exactly identified. All these equations are exactly identified. Let us use this. What is k? K is 3 minus number of 1 greater than or equal to y1, y2, y3. 3 minus 1. Exactly because 2 is equal to 2. Second equation 3 minus 2. That is greater than or equal to 1, 1, 2. 2 minus 1 is equal to, so again 3 minus 2, 1 is equal to 1, exactly identified. Then 3 minus 2 greater than or equal to 2 minus 1, exactly identified. Then 3 minus 1 greater than or equal to 1, 2, 3, 3 minus 1. So all the equations are exactly identified using the order condition. Now let us implement the rank condition. To implement the rank condition, we write the coefficients of the variables in the form of a matrix. You can write the intercept, or you can ignore this. y1, y2, y3, y4, x1, x2, x3. So, in the first equation, minus beta 10, y1 is, coefficient of y1 is 1, coefficient of y2 is minus beta 1, 2, y3 is minus beta 1, 3, there is no y4, minus gamma 1, 1, 0, 0. If a coefficient, if a variable is not present, you write the coefficient as 0. Minus beta 20, y1 is absent in the second equation. 1 minus beta 2, 3, 0, minus gamma 2, 1, minus gamma 2, 2, 0. Then third equation, minus beta 30, minus beta 31, 0, 1, 0, minus gamma 1, 3, 1, minus gamma 3, 2, 0. Fourth equation, minus beta 40, minus beta 41, minus beta 42, 0, 1, 0, 0, minus gamma 4. This is the coefficient of the variables in the simultaneous equation model. Now the definition is of rank condition is an equation is identified if we can construct a non-zero determinant of order m minus 1 from the coefficients of the variables excluded from that equation but included in the other equations. So let us see how we identify the first equation. So we consider only the variables excluded from, to identify the first equation. We suppose that mentally you strike the first equation and you write the entries in which zeros appear in the first. So as you can see, in the first equation, 0 appear here. So it is 0, 0, 1. Then 0 appear here. Minus gamma 2, 2. Minus gamma 3, 2, 0. Then 0, 0, minus gamma 4. This is the matrix. Matrix of the coefficients excluded from that equation but included in the other equations. If a variable is excluded, its coefficient will be 0. So to identify the first equation, you strike out the first equation, then pick up the columns with the zeros corresponding to that equation and formulate a matrix. Then the matrix will have. Now the question is, if the determinant of this matrix is not equal to 0, or if the rank of this matrix is not equal to is equal to m minus 1. Rank m minus 1 means rank, this is a system with 4 equations. So m minus 1 here is equal to 4 minus 1 is equal to 3. So if this is a 3 by 3 matrix, if the rank of this matrix the rank of this matrix can be 3, and we can evaluate the rank using determinants. As it is a 3 by 3 matrix, you just evaluate whether the determinant is 0 or not. And as you can see, 0, if you expand along the first row, is into this, then this into this, this with this into this into this, 0 with this into. That means if you take the determinant of A is equal to 0. So the first equation is not identified. Because rank of this matrix is less than 3, first equation is not identified using the rank condition. Let us see the second equation. In the second equation, 0 is here. So 1 minus beta 3, 1 minus beta 4, 1. Then 0 here, 0, 0, 1. 0 here, 0, 0, minus gamma 4. Again, as you can see, the determinant of this is equal to 0. So the second equation is not identified. Now let us consider the third equation. 0. So minus beta 1 to 1 minus beta 4 to. Then 0 here. So 0, 0, 1. 0 here. 0, 0 minus gamma 4 to. Again, you will see that the determinant of this matrix is 0. That means the third equation is also not identified because rank of this matrix is less than 3. Now consider the fourth equation. Fourth equation. So 0 here, minus beta 1, 3, minus beta 2, 3, 1. Then minus gamma 1, 1, minus gamma 2, 1. Then minus gamma 3, 1. Then 0, minus gamma 2, 2, minus gamma 3, 2. These are the columns with the zeros. As you can see, determinant of this matrix is not equal to 0. So the fourth equation is identified. The fourth equation is identified. So remember the procedure is rewrite the system like this. Formulate a matrix of the coefficients of the variables. Then to identify any equation, if it is first, strike out. Then pick up columns with the zeros. Then if you can formulate a matrix of order m minus 1 from these columns, this we have already strike out from these columns, then the equation is identified. Otherwise it is not identified. Now as you can see, using the rank condition, we can say whether the equation is identified or not. It will not tell us whether it is over-identified or not. So let me redefine identification condition like this. Rank condition tells us whether an equation is identified or not. Identified or not. Order condition tells us whether it is exactly identified or over-identified. Rank condition tells us whether an equation is identified or not. Order condition tells us whether it is exactly identified or over-identified. So remember this point. Rank condition tells us whether an equation is identified or not. Order condition tells us whether it is exactly identified or over-identified. But remember this, when we consider a large simultaneous equation system, evaluation of the rank condition will be difficult. So the question is it a serious problem if a rank condition cannot be satisfied or evaluated? Here, as Harvey says, order condition is usually sufficient to ensure identifiability, and although it is important to aware of the rank condition, a failure to verify it will rarely result in disaster. So, order condition is usually sufficient. Even if you fail to verify the rank condition, it will not lead to disaster. So in the subsequent classes, we will consider a few more examples of identification and also some additional points. Before concluding this session, consider these points. If k minus k greater than m minus 1, and if the rank of the A matrix is equal to m minus 1, the equation is over-identified. 2, k minus k equal to m minus 1, rank of A equal to m minus 1, exactly identified. Then k minus k greater than or equal to m minus 1, rank of A less than m minus 1, under-identified, then k minus k less than m minus 1. Then in this case, rank of A will be less than m minus 1. It is under-identified. There is no doubt about this. Remember these points also. Over exactly, even if this is satisfied, not identified. This is a case of under-identification. Further explanation is not required. So this is the rank condition. And in the next class, we will consider a few more examples and also some additional points of rank condition and order condition, and also the link between these two conditions.